Yes.
Yes. So I'm going to introduce you the title and your affiliation. Then I'm going to briefly introduce your background in this slide. Then I will finish my screen sharing so that you can take over from me. So I'm going to show 2 slides before your presentation. Then after you take over from the screen sharing, you do your slide presentations. Then after that, perhaps our staff will take sort of group photos. You just open your video screen so that our staff will take several shots to keep the record of who attended the seminar. And then you, after question and answer sessions, you finish your screen sharing, then I will take over for additional 2 slides to introduce the next seminar. Is it clear?
Yes, of course.
Yes. And then I will have a full screen. Yes. Do you see the full screen of your photo and title?
Yes.
Yes. So it's exactly 5 o'clock now. So is it okay?
Yes. We can start.
For you to start the seminar?
Yes. Of course.
Okay. Okay, good afternoon, students and professors. I'm really happy to open today's seminar with Professor Doron Auerbach of Bar-Ilan University, Tel Aviv District, Israel. And as you may know, many of you perhaps know his name. He is one of the top electrochemists, especially in battery and the storage areas in the world. And we are very, very happy to have you this afternoon with our students. Let me briefly introduce Professor Auerbach. He got his BS degree from chemistry by Bar-Ilan University with magna cum laude in 1978. Then he got his master's degree in 79 from the same university in physical organic chemistry, this time even summa cum laude. Then he got another BS degree while he was pursuing PhD degrees, this time from chemical engineering, again summa cum laude of Israel Institute of Technology. Then finally he got his PhD from physical organic chemistry with the highest distinction from Bar-Ilan University in 1983. Immediately after his PhD, he went to United States in Case Western Reserve University as a postdoctoral research fellow, working with Professor Ernest Jaeger. Professor Jaeger is another pioneering electrochemistry in many years back. Then he returned to Israel, starting as a lecturer, then senior lecturer, associate professor, then finally full professor from 1985 through all years, then became full professor in 1996. Then he also in charge of Center for Energy Sustainability at Ireland University. And he got many awards, but I'm going to limit only 5 because of time limit. And the important medal he got was gold medal of the Israel Chemical Society 2020 and Samsung Prime Minister Prize for Innovation in Alternative Fuels for Transportation in 2019 and Prompkin Medal of International Society of Electrochemistry. This is the most highest prize from ISE. Then he got A.J. Bard Award of Electrochemical Society in 2017. Then 2014 he got Ernest Yeager Award of the International Battery Association. He is currently a fellow of ECS, MRS, and ISE, and he has published more than 750 papers. And he has more than 67,000 citations. This is from Web of Science with H index of 126. And his research interests are electrochemistry with an emphasis on non-aqueous electrochemistry, high energy density batteries, supercapacitors, energy storage and conversion, power source for electrical vehicles, energy storage for load leveling applications, and so forth. And we are very honored to have you today. And now it's all yours, Doron. Let me finish this. Yes.
So good. I'll share my screen.
Okay, wonderful.
So you see my screen?
Yes. Very good. Somehow.
So I will start. So I really thank you very much for this invitation. I have to say that I like very much the civilization of South Korea. I have a lot of collaborations in Korea, in South Korea. During the last years, I spent months in Seoul with collaborations. Also, I have some affiliation with the DGIST in Daegu. So I'm really happy and honored to spend this afternoon with you. So I'll talk about most suitable rechargeable batteries for electromobility, how to reach the right selection. I should mention several officers from my group here, the list, the left side. We have a nice collaboration with General Motors, with BSF, with ATL in China, in Japan, Quora in the US. So we have support from many sources. Also, I should mention that in Israel, we have most of energy-related research groups are gathered under the umbrella of INREP. INREP is the Israel National Research Center for Clinical Propulsion. So in Israel, in the field of electrochemistry, we turned competition to collaboration, and 28 research groups from 7 Israeli prominent academic institutions are working together to solve very serious energy problems. And I'll share with you some of them. So as an introduction, we talk about batteries today, and we have 4 major uses of rechargeable electrochemical power sources. We have the needs for portable devices, mobile electronic communication, etc. Then number 2, we have electromobility in electric cars, emphasis on high energy density, some compromise with high durability. We need long cycle life and zero for safety. And here lithium-ion batteries should lead together with hydrogen economy, propelling vehicles by fuel cells. Then we have another challenge, also related to electromobility, which is we need very high energy density batteries for unmanned aviation, drones, and robotics. It's also electrochemical propulsion, but with unmanned vehicles. And now we face a great challenge, which is the large energy storage. If we really want to use sustainable energy, we have to store huge quantities of material of energy. We're talking about many terawatt hours, which means huge amount of materials. Here we have to use abandoned element. Lithium-ion batteries cannot work for us. They will go to the roads, to electromobility. At the moment, we want to extract the maximum from lithium and lithium-ion battery from transportation in order to promote the electromobility revolution. Now, fortunately, we are in the academic field. So fortunately, progress requires hard work on basic scientific aspects. So here, there is a very, a priori, you have to keep very interesting, nice, and promoting balance between basic science and the practical aspects. And I think it makes the scientific work very interesting and also challenging and also helpful. So when we talk about cars, what are our options to propel cars? So we have hydrogen fuel cell, not too bad. We have battery electric vehicle. We have hybrid electric vehicle and biofuels. I believe that biofuels is not an option because we simply eternize the problem of burning fuels. With the I would say with hydrogen air fuel cells also, there is still issues of durability, although there is a progress there as well. But it looks that at the moment the most important option is lithium and lithium-ion batteries. Now, when we talk about electromobility and electromobility revolution, and always there is the question if we want to use propulsion by internal combustion engines or by electric vehicles. So even if we produce electricity by coal, we still can put the power station in remote places far from the urban areas. And when we think about the conversion of electricity to electromobility, we see that we have a relatively high efficiency. Overall efficiency from fuel to transportation is definitely more than 30%. While with the propulsion by fuels, by internal combustion engine, the overall efficiency is less than 30%. So we win here. We win here also with the energy balance. And of course, if we move more and more to green energy, to sustainable energy, renewable sources like sun, the wind, no question that electromobility becomes more and more important. Talking about electric vehicles, we have to understand the needs. First of all, electromobility is not a new idea. The first cars from about, I believe, something like maybe 120, 140 years ago, were electrical. We had batteries, old batteries that propelled cars like this. But now we have more modern models. So we have to understand the electromobility revolution. We cannot use the car. The car, we have billions of drivers that used to drive a car with all the accessories, with all the facilities, with air conditioning. We cannot change the car. So within the space of a car, we have to put enough energy to compete with internal combustion engine and with the gasoline. So we have, if we take out the internal combustion engine and the tank of gasoline, we have something between 300 or 500 kilogram or 150, 250 liters where we can put batteries. in order to propel the car. And of course, our challenge is to come up with a long distance. A major challenge is not to compromise on long distance drives. So we want that between charge to charge, we'll be able to drive hundreds of miles. So if we think about batteries for electric vehicle, the final form of the battery is complex. There's cooling and electronics, but everything starts with single cells. We use single cells in order to control heat dissipation, and then we don't use large batteries because of thermal issues. So each car battery is composed of many small cells which are combined in series and in parallel in order to provide a relevant voltage. We're talking about several hundred volts in order to have good effectiveness of the electrical engine. These are organized in modules. And the question is now, which chemistry we can put here? So electrochemistry and material science is the bottleneck, is the key issue. So with electronics, with the mechanical engineering, with cooling engineering, the sky is the limit. The real challenge is chemistry and electrochemistry. And we'll talk about what can be the best materials that will bring us to the desirable energy density. And we're talking about we want to have something like 80,000 watt hours in the car of energy. And this has to be confined in this volume and in this weight. And if we have batteries of that size that contain 80,000 watt hours, then we can drive more than 500 kilometers between charges. Now we are talking about reality. So this is a trivial slide showing different typical cars with photographs of cars that are already running. So I believe that all the car makers in the world have already models of electric vehicles of different kinds, starting from stop-start with small batteries up to full EV, where we have indeed batteries of 80,000 watt-hour in the car that can drive hundreds of kilometers on let's say on electrochemical energy. Now the field develops very nicely. I just take some time, a time slot of 50 years, and in fact we continue with this slope, positive slope of lithium-ion batteries. We see that with the years, starting with lead acid, nickel metal hydride, now we move to lithium-ion batteries with the energy density which reach 250 watt-hour per kilogram. And in fact, with the next generations, we can even do better. In terms of voltage also, we operate now the lithium-ion batteries that can reach 4.5 volt, and this is very helpful because for electromobility and for the electrical engine, we need to combine batteries in series, and as the voltage is higher, we need less batteries in series, which is good. In terms of structure, so the batteries are made of electrodes. We have current collectors, which are copper for the negative and aluminum for the positive, separator in between. We can have this type of either prismatic cells or pouch cells. We can fold we can arrange the electrodes together in a compact manner, and then we shock with electrolyte, the separator. And today, the production of lithium-ion batteries is very simple. We have now full automation, and fortunately, we can really produce billions of cells. It's not enough for electromobility. We have to increase our production capacity, but we solve, I believe that all the engineering problems on the way of high mass production are solved. Now, looking into lithium-ion batteries, In lithium-ion batteries, we gave up lithium metal. We'll get back to lithium metal. We'll see. I'll discuss lithium metal, but I was involved in the development, in first development of lithium-ion batteries. I was involved in understanding the surface chemistry and the limitations. And the revolution of lithium-ion battery technology was to give up lithium metal, which means giving up 90% of the specific capacity, going from nearly 3,070 700 from 3,700 milliampere hour per gram to nearly 370 milliampere hour per graphite. So we gave up 90% of specific capacity at the negative electrode, and but we gain a long life and safety. When the process is not lithium deposition, but rather intercalation of lithium into graphite, then we can have better steady state situation. I should say that within systems comprising lithium carbon compounds and lithium transition metal oxide and the organic electrolyte solutions that we use, and we will discuss some of the organic electrolyte solutions. There is no thermodynamic stability, never. So lithium-ion batteries are always metastable. They lean on very complex passivation phenomena that we'll discuss them later on. So we're talking about very delicate passivation phenomena that allow the operation of lithium-ion batteries. The limit, we could really give up the specific capacity of the negative, because what is limiting is the positive. So what I show you here is major structures and major presentation of cathodes by voltage as a function of the discharge capacity. So we see that the voltage profiles of the structures, we have here, this is a spinel structure, these are layer structure, this is olivine structure. Each structure, when we have a layer structure, we have two-dimensional diffusion. Here we have three-dimensional diffusion, and here we have one-dimension diffusion in the olivine. And the voltage profile really provide very good hint about the process. Let me just close the door here. There is a noise from outside. Just a minute. Sorry, I get back. So electrochemistry and electrochemical response is much more sensitive than XRD, than spectroscopy, microscopy. From the electrochemical response, we know what type of electrochemical reaction we have and what type of phase transition we have. For instance, when we have sloppy type voltage profile, we mean that we have a solid state solution formation. Whenever we have plateaus, we have a phase transition. So from the voltage profiles, we know a lot about the electrochemical process. And as you can see, we have several options with several capacities, and we'll discuss some of these options. In terms of if we think what we have now, so looking at the portfolio of lithium-ion batteries, we have lithium titanium oxide. These are used for negative electrodes. We have lithium, LFP is lithium iron phosphate, LMO is lithium manganese oxide, and NMC means nickel, manganese, cobalt combination. We'll discuss this. We have LCO is lithium cobalt oxide, and NCA is nickel, cobalt, aluminum. And these are the electrodes, and the electrode, and these are the energy density that can be reached with this electrode. But this is what we have now. We can do much better. We are coming now, and I'll share with you data about advanced electrode materials, and we can go further. So I'll skip this this slide. We show more comparison, and I'll also skip this slide with compare energy densities, because we are going to in my talk I will concentrate on the frontier. So what is the frontier? We have the family, which is called nickel-rich NCM. And you see here the formula. We have lithium stoichiometry is 1. Nickel, cobalt, manganese together, again, is 1, and oxygen is 2. And with this stoichiometry, we charge the cathode up to 4.3 volts versus lithium. Now, as we increase the amount of nickel, and we can go even up to 100% nickel, coming to lithium nickelate, then we increase the specific capacity. But we also increase the instability. So if you look, when we increase the amount of nickel, we can increase the distance of driving because we have more specific capacity and more energy. But the particles are cracking, they are stressed, and we have unstable morphology of the particles. But we can overcome it by doping. I'll show you when we dope these compounds with foreign elements, mostly multivalent elements, then we can stabilize the structure and we can make them more stable so we can have longer distance. So a better and more comprehensive presentation is the next one. We concentrate on nickel, lithium, and nickel-rich NCM. This is the general stoichiometry. So, and as we go on this road, we go up with the concentration of nickel. So we have NCM 111 means 33.3 percentage of nickel. We go to 523 means 50%, 622 means 60%, 811 means 80%. We can go to 90% and finally to 100% nickel with LNO. And the energy density increase and increase. The capacity, physical capacity increase and increase. What is nice about this family that we can reach the maximal capacity upon charging up to 4.3 volts versus lithium. This means that in order to extract the maximal capacity, we don't have to endanger our electrolyte solutions. But as we go up and up with the percentage of nickel, the road becomes more problematic. We have cracking, we have instability because of the phase transition. And usually when we have electrochemical instability, we have also thermal instability. Here you can see results of studies by ARC. So if we have small amount of nickel, only 33%, the pouch cell can survive thermal runaway. But when we increase the amount of nickel, we have catastrophes because of instability. So what we do? We use doping. In fact, and when we talk about doping, which means that we add to these materials, we add foreign elements like zirconium, magnesium, titanium, aluminum, silicon, tantalum, and we can use less than 1%, is effective enough. So this doping change the structure. We can do the doping by two ways, by top down and by bottom up. When we talk here, I show an experiment where we look very fast about the effect of different dopants, and the preparation is relatively simple. We take materials, even commercial materials, and we put them in a solution containing the alkoxide of the metals. We dry, so now we have coating with the alkoxide, and then heat treatment at the high temperature destroy the alkoxide, the anion, and now the cations simply go inside, and we have a diffusion of the cation inside, and by line screening, by cross-sectioning, we can really analyze, we can realize that we have foreign elements, so the doping is successful. I should say that doping also affects the surface. Since the last, the final process is heating, we have segregation, and so doping also strengthens the surface very much. We have changes on the surface which are important. What is nice that whenever we get a good stability. And now here, the chart shows cells where we have different electrodes, the same material but with different dopants. And here we compare capacity and we cycle it over hundreds of cycles, and you can see that very, very clearly. We see difference. We see that the reference without doping have very fast capacity fading, and then some dopants are better than the reference. Here in this experiment, the best doping was by tantalum. And interestingly, when you have good doping and when you have good electrochemical stability, it affects the structure. So if we do in situ XRD measurements, and we measure what happens to the parameters during a cycle. So when we charge from 3.7 up to 4.2 volt, and we see changes in the C axis of the cell unit, we see that indeed, for instance, with tantalum, where the most stable behavior, also we have stable structure as well. Another option is here I show doping with niobium, tantalum, tungsten, aluminum, and here we are using the so-called bottom-up approach. We mix upon the preparation with the precursors, which contain lithium hydroxide and the oxides of the hydroxide of the transition metal in the right stoichiometry. We add also 1% of oxide of the dopants, and with the heat treatment, we reach doping. So here you can see a cycling test in full cells versus graphite during several hundreds. So the reference has pronounced capacity fading, and with doping, we stabilize the material. The stabilization is well reflected by differential capacity curves. We see the stability of the voltage profiles. This is a derivative presentation of the voltage profiles during 120 cycles, and we see the stability of the voltage profile compared to reference. And whenever we have electrochemical stability, the thermal stability, we measure thermal stability by differential scanning calorimetry. We put a measured amount of cathode material with electrolyte solutions together, the standard electrolyte solution, and we measure, we now increase the temperature, and we measure when thermal reactions start and what is the heat evolution from the sample. And you can see that indeed, when we have good dopants, like in the case of titanium and aluminum, compared to the reference here, this is the reference, the black one here. We see very clearly that with undoped material we have lower temperature, onset temperature, and also the heat evolution is always higher when the material is less stable. But what is most important is the structural stability. So what I show you here in the right corner, I show you here, we take electrodes, and by focused ion beam, we cut it in the middle. So we have now cross sections of particles, and we look at the structure by scanning electron microscopy. And we see that when we have doped material, after hundreds of cycles, the cross section is smooth. We see that we retain the initial smooth and uniform morphology, while with reference materials, when we have fast capacity fading, we have a lot of cracks. We see the morphological instability. So we have very nice correlation with the chemistry, morphological studies, and thermal studies. Now I move to another family. Very interesting family. Here we're talking about the lithium and manganese rich NCM. So here we have the same five elements, but we change the stoichiometry. So we have again lithium, manganese, nickel, cobalt, oxygen. But now we have lithium, the stoichiometry of lithium that was previously 1, now is 1. It can be 1.113 or up to 1.2. The manganese is at least 0.5, and the rest is nickel and cobalt. We leave oxygen at this stoichiometry. So we call these materials manganese, lithium and manganese rich NCM cathode materials. And here we have very interesting situation. It appears that we can reach very pronounced specific, very high specific capacity. Look, we have here 250, and we can really approach, we can approach even 300 milliampere hour per gram, which is the maximum that can be obtained by intercalation of lithium into transition metal oxide. The secret here, so here you can see the voltage profiles. Here you can see a first process where we activate the material. It appears that whenever we have these materials, we always have two phases, at least two phases. When we have a superfluous of lithium, as an extra lithium, we form the lithium 2 MnO3, this phase, and the rest is the usual active, electrochemical active NCM cathode material that work normally. We need the high potential charging in order to activate this material, and what we activate, in fact, we allow now the oxygens, the oxygen atoms, which are -2, they also they can undergo redox activity, and this redox activity of the oxygens is the source for the high capacity. So here the key issue, in order to stabilize this material, oxygens, if you turn oxides to peroxide, the oxygen become very reactive with the electrolyte solution. So here the key issue is coating. We have to coat the material with buffer zones, and we can do it through the solution chemistry. We can do it by ALD processes. We can do it by gas treatment. The idea is to form good buffer zone on the surface, avoid any contact between oxygen and the electrolyte solution, and also avoid the release of oxygen due to oxidation of the oxides in the material. And I show you two examples. One example is using ALD. We use aluminum oxide compound with lithium or sodium, and we form a buffer zone with a thickness of several nanometers, and we revolutionize the results. So what I show you here is cycling results of cells. It can be pouch cells or coin cells. During hundreds of cycles, here the electrode can be lithium or graphite, and we compare coated material with different alumina, lithium alumina, sodium alumina, and we see big differences. So what we do few cycles at a low rate, so we have the very high capacity, which is nearly 270 milliampere hour per gram, which is very high, and the reference is lower. And when we increase the rates, we do experiments even in 3C rates, which means discharge and charge during 20 minutes, then we see very nice differences between the untreated material and the treated material. So here, judicious coating do a good job, and whenever we have such stabilization, we stabilize the voltage. So here you can see the effect of coating, effect of useful coating on the voltage. We stabilize the voltage. We stabilize the hysteresis between discharge and charge. And whenever we reach this, we also have a good thermal stability. So here you can see different comparison of heat evolution in DSC, in differential scanning calorimetry, of cathode materials with electrolyte solutions. And you can see the difference. When we have a treated material, the heat evolution is much less compared to untreated material. So it's nice to see the correlation. And now let me move to another example. Another example here, we did gas treatment. It appears that when you apply, you heat these materials, you heat this material with this stoichiometry in atmosphere of SO2 or ammonia, you change the surface. You strengthen the surface. There are compounds which are formed on the surface. In the case of SO2, there are sulfide and sulfides, and they form networks. So we have protection. We have a buffer zone, but we have also good transport of lithium ion through the films. And the operation is in an oven, going up to several hundred degrees centigrade in the appropriate gases. And we found that by double gas treatment, we start with SO2, and then we go further with ammonia, we have much better results than, of course, if we don't do anything, or we use only ammonia or SO2. So here you can see some results. In this chart here, this chart shows specific capacity at high rates. It's 1C rate is considered high, fully charged discharge within an hour, which is not too bad. And we definitely see that the double treatment show a better stabilization of the capacity compared. And here also again we do experiments at high rate, but also at low rate, and you can see that we have capacity fading of the untreated material. Here you see a comparison by the histograms. So the green histograms demonstrate the discharge capacity during 400 cycles. There is capacity fading, but here the capacity fading with the treated material is much less. And whenever we stabilize the capacity, we stabilize the voltage. Here, this is the voltage stabilization compared to the other samples. This is untreated. This is treated with ammonia, treated with SO2, and this is the double gas treatment, which is effective. So we stabilize the voltage, and also we stabilize the hysteresis between charge and discharge is lower. And whenever we have such a good electrochemical results, it reflects also in other measurements. So we look at the gas evolution using the online mass spectrometry, and we demonstrate that the gas evolution, and here when we have untreated material, there is evolution of oxygen, and oxygen oxidize the solvents and other materials to CO2. So we see definitely that we compare between the double gas treated and untreated material, and definitely we see stabilization of the treated material. Of course, heat treatment and the DSC measurement show advantage. Compare between the double gas treated material and the untreated material. Look at the black chart here and the green chart. You can see a very pronounced difference, which demonstrate very nicely the stabilization, the thermal stabilization. Now, when we look at another important parameter, we take the negative electrode and we look how much transition metals we have on the negative electrode. Now we can measure the level of dissolution of transition metal from the cathodes to the electrolyte solution. This is a big problem because when we have, usually with all this cathode material, we have dissolution of the transition metal cation, and they go to the negative electrode. We have deposition of transition metal there. It's like needle, and they destroy the passivation of the negative electrode. So we see, if we look at we compare between double gas treated and all the other samples, single gas treated or untreated, we see that with the double gas treated always we have much less dissolution of the transition metals, which means that we have better passivation of the negative electrodes. And after 400 cycles, we do postmortem analysis. We look at the materials and we examine to what extent the morphology of the cathode material remain unchanged. And indeed, when we have electrochemical stabilization, the morphology is also being is stabilized. So comparing untreated material and other and single gas treated materials, we see that the double gas treated, what we consider as a winning process, leave the morphology very stable, in a very good correlation with all the other measurements. So it's nice to see here that we have a coherent results from different channels. So the stabilization effect is clear and is understood. Now, going further to very high energy density. We want to use high energy density systems for drones, for unmanned vehicles, and now we have to introduce back. We go back to lithium. Now, I myself gave up lithium about 22 years ago after working years on lithium metal-based batteries, and after I developed even commercial rechargeable lithium metal battery, which was very nice at that time, 22 years ago, or even 25 years ago. But I gave up because I realized that with lithium metal, we have troubles. The major issue is we have dendrite formation. We have passivation, which is not complete. So we have the cells become dry. We have inevitable side reactions, and it appears that using lithium metal is very problematic. But then during these 2 decades, we have development, and there are approaches how to protect lithium metals. Our favorite is this one. And there are several, I listed here several options. You can read it. But it appears that using electrolyte solutions, which contains functional co-solvents, mostly fluorinated co-solvents like FeC and DFeC, these very reactive solid molecules react on the surface and stabilize very nicely lithium surface, and we can have very nice stabilization. So what happens with lithium? Lithium is always covered by surface film. When we dissolve lithium, then there's no way that the surface films will be flexible and uniform. So we always have places where we have cracks, and there's breakdown of the surface films, which means that we expose lithium to electrolyte solution, and then we have side reactions. So we have breakdown and repair, and this means that we lose more and more the electrolyte solutions. When we deposit lithium, we never have a uniform situation, so we form dendrites. And dendrites are very problematic. Again, we expose fresh lithium and a lot of side reactions. So what is the ideal situation? Ideal situation that you should have uniform surface film. So we leave what we have usually, and we go to the optimal situation at the right side. We want to have surface films which are flexible and accommodate well the changes upon deposition and dissolution. And it appears that we can reach it. So what I show you here, this is results from symmetric lithium cells. So we take lithium cell and we use electrolyte solution that contain FeC as a co-solvent, fluorinated co-solvent, and we have unique surface reactions on the lithium. We form exactly our ideal surface films. And now we can cycle thousands of cycles, and we measure the voltage profiles of the symmetric cells, that we see how they're stable. So this is an experiment that took thousands of hours, and so this is a continuum of voltage profiles that we measure. When we use conventional electrolyte solution based on this solvent, ethylene carbonate, we see the voltage profiles are unstable, and we look at the morphology after hundreds or thousands of cycles, we see catastrophe, while here we keep the morphology relatively stable, thanks to the unique surface chemistry that we'll discuss. Now we can go to high energy density batteries. Simply take the nickel-rich materials that we discussed before, like NCM 60% nickel, 80% nickel, and even 100% nickel, LNO, and we demonstrate that when we use conventional electrolyte solution, we have failure. But when we use our favorite solutions, we have stabilization, thanks to unique surface chemistry on both the positive and the negative electron. So what is interesting is the surface chemistry and the unique chemistry that we develop. And I show you here results from measurements of the electrolyte solutions before and after cycling. Now we have in our systems two sources of fluoride. We have fluoride in the fluorinated co-solvent, and in the lithium hexafluorophosphate, the salt and ion. So we have initially a ratio between the fluoride of the solvent and the fluoride of the salt, and we measure it by flow 19 NMR. So we have initial, now when we cycle thousands of cycles with the symmetric lithium cells, of course we have some consumption of the FEC, but and the ratio changes a little bit, but not too much. Still we see that we have the FEC, live FEC, but when we have cells, now full cells, with the nickel rich NCM cathodes, we have crosstalk between the electrode. The ratio, even after 440 cycles, we have change in the ratio. It is 1 to 3.77 instead of 1.2072 in the original solution. So we see that we have crosstalk among between the electrode. Now we add another co-solvent. Now we have both of them in solution, and we have extra stabilization. This is results related to 80% nickel, and these are experiments that were carried out at relatively fast rate. So this is nice result, and we demonstrate stabilization thanks to the presence of two co-solvents, compared to solutions where we have only one co-solvent, only FEC. And now with both of them, we see stabilization, and the electrodes remain very stable. Now going to the more challenging situation with LNO, we start with very high specific capacity, 250, and this is only by charging up to 4.3 volts, no more. We have some capacity fading, but we can stabilize the material during hundreds of cycles up to lithium metal when we have this type of electrolyte solution. And thanks to the unique surface chemistry that we have on both electrodes, we stabilize the situation. Interestingly, the impedance they become smaller and smaller because of compactization of the surface film during cycling, and the cathode material are untouched. If you take untreated material, you have cracked cathode material, the morphology is changed, but thanks to the unique surface chemistry, by XRD and by morphological studies, we demonstrate a very nice stabilization. So now, more examples, even at 55 and 45 degrees, using the combination of FEC and DFEC, we have very nice stabilization even at elevated temperature, and we can even use very small amount of electrolyte solution per milligram of cathode material. These are nearly practical amounts, and even at 55 degrees C, we demonstrate stabilization, even if we have only one microliter per milligram of electrode material. So we see that by using more than one co-solvent, we can even stabilize the system further. And now we work on a portfolio of fluorinated co-solvent, and it appears that this is a very important, I would say, solution chemistry that can help the field very nicely. So now we can come to the chemistry by spectroscopic measurements. We understand more or less what's going on. And I don't want to go over this scheme, but you can find it in the literature in our papers. But because of the presence of fluoride we have reactions that form polymeric matrices. So we have polymeric matrices in which we have ionic compounds like lithium fluoride embedded. So we have matrices that contain oligomers and polymeric species. This gives the flexibility, and we have inorganic species, ionic lithium compounds that maintain the good mobility of lithium ion through the surface film. So we have here complex surface chemistry with a lot of options, thanks to the fluor atom. So we can dehydrofluorinate. We form double bonds on the surface, and we have polymerization on the surface. And this option to have polymers on the surface, either through the double bond or through the carbonate groups, we reach the right, let's say, structure and behavior of the surface film. So now we can come to this cartoon, and I'll concentrate on the right side. When we have the two fluorinated co-solvents, FeC and DFeC. What we found is the following. The DFeC is the most reactive, so first of all, it is consumed and it forms surface film. But now upon cycling, we have a change, in the morphology, we have cracking, the surface films are not always stable, so we have FeC. The FeC now, the FeC reacts as a healer. So whenever there is any weakness in the surface film, FeC is reacting, and so we have, and we were able to demonstrate or to show results by spectroscopy, XPS, and FTIR. So I understood this. We did this stepwise studies, and came up with the understanding what's going on. So we have this mechanism of healing. We have first of all, DFeC is reacting, but then we have FeC that heal the cracks whenever there is instability in the surface film. We have reactive FeC that repair the material. So now we can go to more interesting materials, like we are happy with stabilization of the lithium side. Now we can go to 5-volt system. So LNMO is a lithium nickel manganese oxide spinel. This is a 4.7 volt cathode material. And here, we need the buffer zone. We have to avoid dissolution of nickel and manganese to the electrolyte solution. So we need coating. We found that by using tungsten selenide, but it's not, we have several, now we have a portfolio of materials that can, we have physics option of layered materials like tungsten selenide on the surface, and we can demonstrate the cycling during even 55 degrees C, and we can see very nice stabilization of the material. We stabilize the capacity, we stabilize the voltage, and it appears that by coating the cathode with tungsten selenide, it affects also the lithium or the negative, the lithium or graphite negative electrode as well. So we have situation where we have buffer zone on the positive, and we have also buffer zone. We have an effect of the layered compound on the lithium negative, and in such a way we have stabilization on both the lithium and the lithium and the cathode material. We avoid detrimental the dissolution of transition metal from the cathode to the solution, and then their deposition on the negative electrode, and in such a way we demonstrate impressive stabilization. Now I want to move to another point. I have two more things to show you when we talk about high energy density system. We know that the usual cathode material that you use in your cellular phone and your computer is LCO, lithium cobalt oxide. In your cellular phones or computers, the lithium batteries based on lithium cobalt oxide are charged up to 4.2, 4.3 volts. And then people thought that it will be unstable and dangerous to use higher potential. But we found that if we go to 4.6 volts, and now we do two things. We use coating. We use aluminum fluoride lithium coating. We can use other active metal here. But take compound comprising lithium, aluminum, and fluoride. It's a fluoride, aluminum fluoride material. So this coating stabilizes the LCO, and then we use our favorite, our electrolyte solution which contain the DFEC and FEC, the two fluorinated co-solvents together with DME. And now we see very nice stabilization, going from barrel CO to the coated material with the nice stabilization, and then by the combination of good coating and the use of right electrolyte solution, we see very nice stabilization, and the stabilization is both on the negative and in the positive. So you can see here, we take lithium electrodes after cycling in such cells, and we compare the morphology of the lithium electrode through post-mortem analysis, and we see very clearly the very nice stabilization effect of the solution comprising the two fluorinated co-solvents based on the surface chemistry and the understanding that I showed you before. Now going further, the question is how far we can charge. So we did different experiments. We even charged up to 4.7 volt, but then we realized that we can charge up to 4.6 volt. We can get 220 milliampere hour per gram. And this is very nice because if we look at we have 220, this is very important. We have 220 ampere hour per kilogram times 4 volt. So we have 880 watt hour per kilogram LCO, cathode, just cathode. Now the question is, what is the number, in which number we have to divide it in order to be realistic? And it appears that if we do good engineering, the number can be 2 point something, something between 2 and 3. But this means that we have a very good chance to reach a specific energy density that is 400 and more than 400 watt hour per kilogram. And this is beautiful. This is very nice. I think here we can really reach the highest energy density, combining lithium metal and LCO, high voltage LCO, going up to 4.6 volt. And here you can see different type of coating. Here we have another type of coating. I don't expose it at the moment, but we see very nicely that even at 30 degrees and 45 degrees C, compared to untreated material using our favorite electrolyte solution, we have very impressive stabilization starting from 225 milliampere hour per gram, which is not too bad. And finally, at this topic, we did the long-term experiments. We use a coated cathode with our favorite electrolyte solutions. We run 100,000 cycles versus lithium metal, and then we open the cell, we change the lithium metal and continue to run. And here you can see experiment without treatment in the reference system. The capacity failing is very pronounced. But here we demonstrated that this is a 1C rate. It's a fast rate. So this is a very nice specific capacity for 1C rate. So within thousands of cycles, we see it's stable, but after 1,000 cycles, we change just the negative electrode, and we retrieve the stability, and now we could run another 1,000 cycles with our favorite coating and with our favorite electrolyte solution. And again, this means that we can guarantee very high energy density for this type of cells. Finally, if we think about a very high energy density lithium batteries, of course, sulfur is a very good option. With sulfur, the specific capacity, theoretical capacity can be 1,600 milliampere hour per gram. And if we compare lithium ion and lithium sulfur batteries, there is a clear advantages in capacity, power. The voltage is lower, but here the low voltage is an advantage in terms of safety. So the question is, what to do? If you use too sophisticated, and we have problem with sulfur. Sulfur is insulating, you have to mix it with carbon. So reaching the theoretical specific capacity of sulfur, which is 1,675 is very, very hard. Very, very hard. So it appears that if we really want to reach high energy density batteries, we have to we have to give up complex structures. We have to use simple cathode with high loading of sulfur, and we need as simple solution as possible. And this is what we did. We demonstrated that if we will use the conventional electrolyte solution for lithium sulfur batteries, this is, by the way, electrolyte solution that we discovered. We worked a lot with lithium metal based batteries with this electrolyte solution, and we demonstrate that the oxalane is a very good solvent. There is unique surface chemistry. You can see it here. The oxalane is reduced to different compounds, and there is the sodium ion. This also is being reduced to several compounds, and we have very complex surface chemistry. When we have lithium nitrate, this is an important additive because this additive oxidizes sulfur, and we have now networking of lithium sulfur oxygen compound on the surface, so it enhances the passivation of lithium. And it appears that if we use a very simple additive, this compound in fact is formed through recycling, but if we leave it, we put this additive from the very beginning. So from the very beginning, the electrolyte solution contains these ingredients and also this active material, the lithium sulfide material. So we demonstrate very nice stabilization of lithium negative electrode. Here you can see results of galvanostatic cycling of symmetric cells without conventional electrolyte solution that are used in lithium sulfur systems. So without our magic additive, we have a failure after some cycles, but with our magic additives, we can demonstrate very prolonged cycling of the symmetric cell. So now we can go to full cells, and indeed we demonstrate that compared to the reference by using our magic additive, which affect the surface chemistry, and we know exactly what it does. Again, we have complex surface chemistry which form networking on the surface and stabilization by flexible surface films that accommodate the morphological change and avoid also continuous reduction of lithium sulfur species, which are formed by reduction of sulfur. We can use encapsulation of sulfur in carbonaceous material. This is carbon cloth, which is highly activated. So we can reach something like 60% sulfur, and coming up with the systems with relatively high energy density under optimization. And now we compare. These are results of cycling test of lithium sulfur cells in conventional electrolyte solution, in encapsulate sulfur within the carbon, something like 60% sulfur within the composite. You see, this is a carbon cloth, and here it means that it's monolithic. In fact, we don't need binder, we don't need a conductive additive. Here we can reach relatively high percentage of sulfur. So without our additive, the passivation of lithium is not strong enough, so we have failure after a few hundred of hours of cycling. But with our additive, when we have a priori the sulfide and now the nitrate in the electrolyte solution oxidize a priori immediately oxidize the lithium sulfide to lithium oxygen sulfur compound, and from the very beginning the lithium is well protected. Now we can come up with continuous cycling. So these are simply continuum voltage profiles during the galvanostatic cycling of lithium sulfur cells, and we demonstrate that here also we can reach a reasonable stability. So I believe that I should say that one I have to, there is people talk about fast charging, and there is a lot of publication about fast charging. And I have to tell you that whenever you use fast charging, it always goes on the account of energy density and number of cycles. So talking about fast charging is, from any point of view, illusion. We have to understand that we need some time for charging. We need what is most important is high energy density and prolonged cycling. And if we go to fast charging, we have to give up both in capacity and also in the cycle. The thermal, in terms of thermal stability and stability in general, we have lithium iron phosphate. Lithium iron phosphate is a cathode with very mild specific capacity. It's only 160 milliamp per hour per gram, and the voltage is 3.5 versus lithium. But it appears that when we compare cells comprising lithium iron phosphate to any other cells, we can demonstrate very prolonged cycle life, order of magnitude higher. We can talk about maybe 10,000 or 15,000 cycles with graphite and lithium iron phosphate, and the thermal stability is much better by far from any other electrode material. So now we can rethink, and this brings me to the next to the next two slides. This is the last slide before conclusion. So people try to think about next generations. So and they show usually this stepwise changes going from third generation, two generation, third generation, solid electrolyte batteries, fuel cells, of course, and then lithium sulfur, lithium oxygen, with a lot of promises. There's a lot of noise from startup companies. Be careful from promising about fast charging. High power always is on the account of high energy. Safety and cycle life more important than energy density. 2.3 volt graphite, lithium iron phosphate batteries are suitable for everything, also for electromobility. So by good engineering, you put enough batteries in the car, use more space, and then be sure with cycle life and safety. Less energy density, more battery in the car, but best safety. And I believe that combination of fuel cells and lithium batteries are going to win the field of electromobility. And now I can really conclude. So electromobility is not a dream. It is real by advanced lithium-ion batteries. We have many options. I showed you high energy density systems and the nickel-rich, lithium and manganese-rich. We have now a very nice portfolio of high energy density options where we learn how to stabilize the materials. There's a lot of noise about novel nanomaterials for batteries. Nano and batteries doesn't go together. Why? Because whenever you have nanomaterials, you have high surface area. We are talking about systems that never reach equilibrium. Everything depends on passivation phenomena. So it's no bringing nanomaterials to the field is very problematic, and we work with micromaterials, not with nanomaterials. So we can offer very good lithium battery technology for both electromobility and large energy storage. If we take graphite and lithium iron phosphate, we have excellent batteries for both electromobility and large energy storage, but we have to leave lithium batteries for EVs. We may not have enough lithium resources for both applications, so lithium will go to the roads, and we have to develop alternative technologies. I think that sodium batteries is a very good option. So nothing beyond conventional lithium-ion batteries is really relevant for electromobility. In turn, fuel cells, hydrogen oxygen fuel cells, are becoming highly important power sources for electromobility. Major challenges are high durability and cost-effective catalysts and membranes. But I can say, since we have a lot of activity in Israel on fuel cells, I'm very happy to see the progress. We see progress. There is also progress in lithium sulfur batteries, but energy density may go on the account of prolonged cycling. So if you really want to have energy density which is high, we have to give up cycling. We need simple electrodes. We can do better. We can progress. Inter non-aqueous lithium air batteries that made a lot of noise a decade ago, they are now very far from practicality. We worked a lot of lithium oxygen batteries, and we learn how complex are these systems, but this is another seminar. We see also nice progress in sodium-ion batteries. This is very important. This field is very important. Fortunately, we can follow with sodium electrochemistry, lithium electrochemistry, and they be very good for load leveling. We don't have any limitation with sodium. We can come up with batteries comprising peri-abundant elements like sodium, manganese, titanium, iron, oxygen, carbon, and I believe that sodium-ion batteries can help a lot with the large energy storage. Too many promises about the fast charging. Ignore the trivial science behind Ragone plots. High power always comes on the account of high energy. So what is the new trends today? after working on so many nice and impressive high energy density systems, engineers of the car makers are giving up more and more energy density, emphasize on cost and element abundance. So lithium iron phosphate, this cathode, which is very moderate in performance, is becoming important, and we may see more and more car makers give up energy density, going to graphite, lithium iron phosphate battery, and gaining, let's say, safety and durability, and by good engineering, they can use for that normal cars. We don't have to revolutionize the car, and yet come up with a really long-term driving. It appears that here also we have gain in the range capability as well. This LFP are relatively fast. And with this, I'm ending my talk. It was a bit long, but I hope that I spoke slowly enough and you could follow me. It's a great opportunity also to, I'm love to share with you our results. All what I showed you came from our lab during recent years. So I'm quite proud of what I showed. And I thank you very much for your kind attention.
Well, thank you, Doron, for your very nice presentation. And now the session is open for questions or comments. First, from students. You can send questions on chatting panel.
Yes, if I can answer the question.
Yes, I know. Yes.
I see the screen, and I can follow question from the chat option.
Well, why they think about questions? I have very minor question for you. And concerning about the fast charging, and I know there are many factors to shorten the charging time. And do you think the optimum or the shortest possible time for charging would be far less than an hour, which is rather common at this moment?
Well, if I can answer, I think that if we give up high energy density, we go to LFP, we go to graphite and lithium iron phosphate. These lithium iron phosphate are relatively fast cathode material because you can work there with lithium iron phosphate. You can really work with some nanostructure, and this is another discussion. Why lithium iron phosphate are so good, although the electrical properties of them, the intrinsic properties are bad, but the cathode are very good. So it appears that today we can think about maybe, for most of drivers, they have enough time to charge the batteries. I think that it's possible now to charge 80% of the full capacity during 10 to 15 minutes. So using 3 or 4 C rates for charging may be reasonable. So I would say that there is a chance, of course, if you emphasize high power density and fast charging, you have to give up energy density. But there may be compromise where you can still drive 200 kilometers between full charging, and now you can shorten the charging time to maybe even between 5 to 10 minutes. So I think, and we have to understand that when we charge fast, it means that we apply high voltage, and we may have the position of lithium on the negative electrode, which is very dangerous. So
that's right. Yes.
Fast charging may be very dangerous. It also shortens. When we deposit lithium in lithium-ion batteries, we add more side reactions, we shorten the life of the battery. So I can see there are compromises. I think that charging a nice piece of enough part of the capacity during between 5 to 10 minutes may be realistic, but not a few minutes, not couple of minutes, no, because again, you can come up with very fast charging, but the energy density will be very low. So maybe for micro mobility, if we think about scooters or bicycles, where the distance between charging are relatively short, then maybe you can come up with fast charging, because energy density is not that important. You don't have to drive long distances. So I would say there are compromises. There is a room for optimization. But we have to be careful. We have to understand what we have to give up when we talk about high rate.
Okay, thank you. And any other questions or comments from professors? You know, it's getting a little bit late here, and maybe many students are getting hungry.
People can send me questions. Maybe people are also shy.
Yes,
so,
that can be done. Yes.
What you can do, maybe you can concentrate questions, and then if you can send me a list of questions from the students, I'll be more than happy to send you replies by email. So I can answer questions by email.
Okay, wonderful. Okay, wonderful. Thank you.
I'll open this option for you.
Okay, and again, thank you for your participation, and we really enjoyed your very nice presentation today, and I hope to see you sometime.
Well, thank you for the opportunity. As I said, I have a very good feeling and a lot of friends in South Korea, and I'm very happy about the opportunity to be in touch with Korean scientists, the Korean students, and the professors. So I'm thankful about that.
Well, I'm going to introduce the next seminar on June 2nd at 4:30 in the afternoon, and this time Professor Jong-Yun Sun of Department of Material Science and Engineering, Seoul National University, will talk about biomimetic approaches with stretchable ionics. And again, students should know that the seminar report is due by noon on June 23rd. You can mail it to me. And again, thank you very much for your nice presentation, Doron. And now, now we will close the seminar today. Okay. Bye-bye. Bye-bye.